In the previous lecture, we discussed about different types of frequency FM signal demodulators. In continuation to that, the next important type of FM demodulator is your PLL. That stands for phase locked loop. It is one of the most extensively used kind of a FM demodulator, and apart from FM demodulation, there are several other uses of PLL circuit as well. So as the name suggests, phase locked loop. So this circuit has to do something with the phase of the signals, right? So we can say that it's a very important device that is typically used to track the phase and frequency of the incoming signal. It can track the phase and frequency of incoming signal. Okay, there's a very interesting relationship between the frequency and phase. You must be aware about it. We can say that if there's a constant phase difference between two signals over the period of time, then we can say that both the signals have the exactly same frequency, and the vice versa is also true. And this is the principle on which the PLL is based. The working of PLL is, you can say, PLL exploits this property or the relationship between the phase and the frequency, because we know that if we, let's say, just for an example, we take a sinusoidal signal and we draw its corresponding phase plane. Okay, if let's say there's a point on the signal that moves along the envelope of this signal, and if we map that point to this phase plane, so we can say that the frequency with which the signal moves over this point moves over this signal is exactly same the rate by which this point moves over this phase circle, right? Now if we take one more signal, now if we say that the frequency of signal A and signal B is same, in that case what can we predict about the phase difference between these two signals? See, the phase is obtained by mapping this point over the signal to the phase circle, right? So if the frequency is same, both the points on both the signals will move at the same pace, same rate, right? So this phase difference will remain constant, isn't it? And the vice versa will also hold. This is the principle which is being exploited by phase locked loop, and the purpose of PLL is to track the phase and the frequency of the incoming signal. That is the purpose of the PLL. Okay, so one of the uses of application of PLL is FM demodulation. Apart from this, there are several other applications of PLL circuit, which includes synchronous demodulation of AM signal, if you remember, in case of synchronous demodulation, a locally generated carrier signal is required at the receiver end. So that part of the demodulator is taken care by the PLL circuit. PLL helps in generating the the carrier signal, which has the frequency and phase exactly synchronized with the frequency and phase of the carrier that was used at the input end. Okay, this is another application. And further, it is also used as a clock recovery system. And clock recovery, timing recovery. So these are some of the applications of the PLL circuit apart from FM demodulation. Now moving on to the basic structure of the PLL circuit. It has three basic components. PLL has three basic components. Let us first draw the block diagram of PLL. So first we have a phase detector. This is a phase detector. Then we have the loop filter. Then in the feedback loop we have a voltage controlled oscillator. Voltage controlled oscillator, or VCO. The output of VCO is given as input to the phase detector. One of the input is the incoming signal, and this is the output. So this is the basic block diagram of the PLL circuit. We have a phase detector, a loop filter, and a voltage controlled oscillator. These are the three basic components of the PLL circuit. Next, let us have a look at the basic operation of PLL circuit. Okay, so the aim of this PLL circuit would be to track the phase and frequency of the incoming signal. Okay, so operation of PLL is similar to a feedback system. In a typical feedback system, we know that the feedback signal, this is the feedback loop, right? In a typical feedback system, we know that the feedback signal tends to follow the input signal. Okay, if the feedback signal, this is the feedback signal, if this feedback signal is not equal to the incoming signal, the difference between them, this phase detector detects the difference between these two signals, difference in terms of phase. Okay, the difference between them, or we can say the error signal, is given or it is used to change the feedback signal until it is close to the input signal. That is the simple working of a feedback system. Okay, I'll repeat once again. It's kind of a typical feedback system. Okay, and in any feedback system, the feedback signal that is coming from this feedback loop, it tends to follow the input signal. And if there is a difference between the input signal and the feedback signal, the difference or the error signal is given as input to the feedback components, such that the feedback signal is brought close to the input signal. That is the working. Okay, the PLL operates on the similar principle, except that the quantity which is fed back, in the loop, or you can say compared in this detector, is not amplitude, rather it is phase. We compare the phase of the incoming signal with the phase of the feedback signal. Okay, and if there's some phase difference, that phase difference acts as an error which is given as input to the feedback circuit, and the feedback circuit changes the feedback signal such that the phase error between the incoming and the feedback signal is minimized. That is the simple operation in simple language. So what happens is the VCO, this voltage controlled oscillator, it adjust its own frequency such that the frequency and phase can track those of the input signal. Okay. So the frequency of the output of this VCO would be omega C plus C into ET. ET is the error signal. Okay, C is the constant of the VCO. Okay, rather it is the error signal after the loop filtering process. Okay, and omega C is the free running frequency. It is the free running frequency. Okay, so when the error is zero, that means the phase of incoming signal and the feedback signal is exactly same, or there's a very constant phase difference between the two. Omega is equal to omega C. That means the frequency of the two, that is the incoming signal and the feedback signal, are same. That is our motive. Okay, we need to find out a signal such that the output of this VCO is having the same frequency as the incoming signal. Now if you take an example of a FM signal, let us suppose that the incoming signal is an FM signal having different frequencies at different instant of time. Okay, the frequency changes with time, right? Now let's say this loop is in the locked condition. That means the frequency of incoming signal and the feedback signal is same. Now suddenly there is a frequency change in the incoming signal since it's a FM signal. Okay, so if the frequency of incoming and the feedback signal is different, there will be a phase change between the two signals. Okay, that phase change will that signal will be given as an error signal out of this phase detector circuit. This error will be given as feedback to voltage controlled oscillator. The purpose of voltage controlled oscillator is what? It generates the signal frequency based on the input voltage, right? So based on this error, which is the phase difference, it changes the frequency of the output signal such that the frequency of incoming and this feedback signal is same, and the circuit again goes in the lock condition. Okay, and here we get the demodulated message signal output, isn't it? So whenever a circuit goes in out of lock condition due to change in the frequency of the incoming signal, again suddenly this feedback loop will become operational, it will become active, and this error between the two signals will be minimized, and again the frequency will be captured and locked. Okay, this is the simple concept of phase locked loop circuit. Okay, now there are two important terminologies in the PLL circuit, which are lock range and capture range. Okay, the lock range, we know that the VCO tracks the frequency, the VCO tracks the frequency and phase of the incoming signal right. So a PLL can track the incoming frequency only over a finite range of frequency shift, only over a finite range of frequency shift, and that range of frequency shift is known as lock range. That means, let's say the incoming signal frequency is 2 kilohertz, okay, and the circuit is in lock condition. That means the feedback signal will also have the frequency that is 2 kilohertz. Now suddenly this frequency of incoming signal changes to, let's say, 10 kilohertz. So there is a significant difference between the frequencies. So error signal will generate and the feedback loop will get operational, and this error will be minimized so that the frequency of the two signal is same, right? But there's a limit, or we can say a finite frequency range over which this circuit can again achieve the lock condition. It cannot, achieve the lock condition if we change this input signal frequency unconditionally. That means, let's say if we change the input signal frequency to, let's say, 1 megahertz, in that case circuit won't be able to again achieve the lock condition. So there's a particular range of frequency in which the circuit can achieve the lock condition once it is gone out of the lock. Okay, that particular range is known as the lock range. And similarly we have another term, that is the capture range. Capture range is that if initially the input and the output frequencies are not close enough, the loop may not acquire the lock in the very first place. If initially the input and the output frequency, the input and the output frequencies are not close enough, then the loop may not acquire the lock in the very first place. This and the range in which the lock can take place actually initially, that range is known as the capture range. The range in which the lock can be achieved initially is called capture range. Okay, that means, let's say if initially the frequency of the input signal is 2 kilohertz and the free running frequency of this VCO is 1 kilohertz. This is the initial most point. Then again this feedback signal will be generated and this circuit will try to achieve the lock condition, and it will achieve the lock condition, right? But let's say this difference between the incoming signal frequency and the VCO output, the free running frequency, is very huge. Let's say this is 1 kilohertz free running frequency and this incoming signal frequency is let's say 50 kilohertz. Then it is not guaranteed that this loop will acquire the lock condition initially. Okay, so there has to be a range of frequency, that is the difference between these two signals, in which the signal can acquire the lock condition. That particular range of frequency is known as the capture range. So this PLL type of the FM demodulator is the most frequently and widely used kind of a FM demodulator. I'll just quickly go through the leftover 2 or 3 types of FM demodulators as well. So the another one is balanced slope detector. In the previous lecture we have already seen the functioning of the slope detector type of FM demodulator. So balanced slope detector is quite similar to that of the slope detector FM demodulator. The difference is that it combines two circuits of individual slope detectors in parallel, and the FM input is fed 180 degree out of phase. So this circuit, you can say this circuit combines two circuits of individual slope detectors in parallel and the FM input is fed 180 degree out of phase. So in case of balanced slope detector, it makes use of two individual slope detectors that we have already seen. I'll just quickly draw the circuit diagram of this. We have a center tapping here. Sorry, this is minus. So yeah, this is the circuit diagram for the balanced slope type of detector. So you can see the center tap winding of the you can say tuned secondary side of the transformer. It introduces a phase inversion. So this center tapping introduces a phase inversion, and as we have seen that in case of slope detector, there was a cascading of the tuned circuit with the envelope detector. The same thing is here. There are two sets of the same thing, a tuned circuit and the envelope detector. Tuned circuit and envelope detector. So there are two sets of each, right? So the tuned circuit, it consists of this inductor LA, CA, right, and LB and CB. These are the two tuned circuits that converts FM input to the AM signal, right? After that, we have a envelope detector that is your diode, capacitor, resistor, two sets of it, right, to detect the message signal out of the AM signal. That is the basic functioning of the functioning remains same, but instead of one, we are using two slope detectors here. So this, obviously the benefit of this was that we get a wider range of frequencies over which the frequency characteristic is linear. So it gives a wide range of operation. That is the point of using balanced slope instead of a slope detector. But there are several other disadvantages of this kind of a circuit, which are difficulty in tuning. That is one of the disadvantages. Second is poor limiting. That means the amplitude variations cannot be limited with much efficiency. Okay, so these are the two disadvantages of it. And next type of the FM signal detector is your Foster-Seeley discriminator. I'll first draw the circuit diagram of it.